Now, seeing as we have been substituting into formulae, this is a nice opportunity to bring in something from physics or mechanics, which is the formula for Newton's universal law of gravitation. The idea being that every particle is essentially attracting every other particle in the universe, and we can calculate that gravitational force by looking at this formula here and plugging into this formula, where G is the gravitational constant, which has been calculated to be 6.674 times 10 to the minus 11 Newton square meters over square kilograms, rather. Then we've got the masses of the two objects that you are looking at, m1 times by m2, divided by the distance squared between them. Okay? Now, what we can do is we can use this formula to actually find the acceleration due to gravity of a falling object, because that force would be looking at the weight of that object, which we can write as mass times gravity. Okay? Now, if we consider the Earth's mass to be, let's say, capital M, so I'm going to replace M1 with capital M and lowercase m to be the mass of the object that is falling, we get this. Now, of course, we've got lowercase m on both sides of our formula here, so actually they can go. And this simplifies down to this. So the acceleration due to gravity will be equal to the gravitational constant, so 6.674 times 10 to the minus 11, times by the mass of the Earth, so 5.972 times 10 to the 24, divided by the Earth's radius squared, because here you're looking at the centre of mass of the Earth, which we directly at the centre, to where the falling object is. Now, if you think about, here's your Earth, here's your centre, and the object that is falling, okay, the distance from the centre of the Earth to the falling object will be roughly the same as the distance from the centre of the Earth to its outer edge, just because the Earth is so massive. Okay, so we can essentially just use the radius of the Earth here. So that's 6.371 times 10 to the 6, and that is squared. So our job here, we've substituted the formula, our job here is to find out what this actually is. So, on your calculator should be able to deal with all of these values that have been given in standard form. So 6.674 times 10 to the minus 11 times by, and then open the fraction, 5.972 times 10 to the 24 over 6.371 times 10 to the power 6, all squared. And you should get 9.8195, etc. So to 2 decimal places, let's say, that's 9.82. Or if we put it to 1 decimal place, we'll probably get the value that we may know. So 9.8, and that's meters per second per second. And so to 1 decimal place. Now, I haven't used exact values here, I've used random values, so generally we usually think of the acceleration due to gravity as 9.81 meters per second, but 9.8 meters per second is fine for a lot of cases, rough cases, that we use in maths. So that is where the acceleration due to gravity, if you have seen that before, comes from.